Hello everyone, welcome to this second class on finite element analysis, and in this class let's try to do this three-step bar problem. And in this problem you can just see the bar is fixed at this node 1 and node 3. So in last class in last problem actually I just solved it in detail, like I just showed the conversion in detail, conversion of this SI units from GPA to MPA, everything. But in this class let me try to solve it in quicker time. So first let's try to write the given data. So given data, let's try to write it. So given data, we have to write it A1. A1 is nothing but area of element 1, that is nothing but 900 mm square, no need of any conversion. And A2 is nothing but found to be 400 mm square. So this is also fine. And A3 is nothing but 200 mm square. It is given in the question itself. Next L1 is nothing but length of element 1, 80 mm, no need of any conversions. So L2 is nothing but 90 mm and L3 is nothing but 70 mm. Next, after this, we have to write the Young's modulus. Young's modulus E1 is given as 70 GPa. 70 GPa, I've just shown the conversion in last video. If you don't know, you can just watch that last video. It is nothing but 0.7 into 10 to the power of 5 Newton per mm square. If you wanted to know how did I get this, you can watch my previous video. And E2 is nothing but 105 GPa. 105 GPa can be written as 1.05 Newton per, into 10 to the power of 5 Newton per mm square. It is not 1.5, it is 1.05. So just keep that in mind. And E3 is nothing but 200 GPa. 200 GPa can be written as 2 into 10 to the power of 5 Newton per mm square. So you can just see all the SI units are in either Newton or in mm or mm square. Okay, now let's try to go to the solution. The step 1 will be to construct the FEA model. So you can, I'm not going to write all those in sentences, so you can just refer the video, previous video itself here also. So let me try to draw this FEA model. So FEA model, it's 80, 90 and 70. So accordingly, let me try to vary the lengths. So this is nothing but a rough sketch. So let me try to write this is node number 2, and you will get 4 nodes over here. So this is nothing but node number 4. So approximately, let me try to do it. So this is node number 1, node number 2, node number 3 and node number 4. So here let me try to indicate the forces. So forces at node number 1, this is F1. Force at node number 2, this is F2. And force at node number 3, this is F3. And similarly, this is force at node number 4, this is F4. So F4. And similarly, this is 1 to 2, this is nothing but element 1. Similarly, 2 to 3 is element 2. 3 to 4 is element 3. Okay, element 3, fine. So we have totally 3 elements, and at each node we will get displacement q1, displacement q2, displacement q3 and displacement q4. And length node 1 to 2 is nothing but length L1, 80 mm. Node 2 to 3 is nothing but element 2, that is the 90 mm. And 3 to 4 is nothing but element 3, that is 70 mm. So I've just indicated all these 3. The next step will be just calculation of elemental stiffness matrix. I'll just write it in short as ESM. Okay, so elemental stiffness matrix K1 equal to A1. A1 is nothing but 900. So all those formula, everything you can just see in my previous video where I have explained in detail. So A1 into E1. E1 is nothing but 0.7 into 10 to the power of 5 divided by L1. L1 is nothing but found to be 80. And the answer is minus 1, 1 and minus 1. So while you are dividing, only just put this in your calculators. The answer will found to be 7.875 into 10 to the power of 5. So once you try to simplify that, you will get it in so much. Okay. So now you can multiply the 7.875 inside. I'll get 7.875 minus 7.875 minus 7.875 and 7.875. And let me just put 10 to the power of 5 over here. So this is nothing but found to be K1. K1 is nothing but, I'll write it over here again, 10 power 5, 7.875 minus 7.875 minus 7.875 and 7.875. So now let me try to do K2, because and in this problem you will get 3 elements. So therefore you will get 3 stiffness matrix, K1, K2 and K3. So now let me try to do this K2. K2 is nothing but found to be A2. A2 is nothing but, how much is A2? A2 is nothing but, you can just see it is clearly mentioned as A2 is 400 and A3 is 200, 90 and 70, L2 and L3 are, and E2, E3 are also given, 1.05 and 2. Okay, now A, we can just try to put A. A is nothing but 400 and E2 is 1.05 into 10 raised to 5 and L2 is 90 and 1 minus 1 minus 1 and 1. So upon simplification, upon all this simplification, I'll get that as 4.667. So if I try to multiply that inside, I'll get like this: 4.667 minus 4.667 minus 4.667 and 4.667. Okay, now so this is K2. And next K3 I'll get it. So K3 is A3 is nothing but 200, and E3 is nothing but 2 into 10 to the power of 5. L3 is nothing but 70, and let me just try to put this minus 1 and 1. So upon simplification, I'll get that as 5.714. So let me just try to multiply that 5.714 inside. I'll get 5.714 minus 5.714 minus 5.714 and 5.714. So this is nothing but found to be K3. So now K1 is nothing but, so we have got K1, K2 and K3. So K1, K2 and K3. So this K1 is nothing but for node 1 and 2, node 1 and 2. Similarly, K2 and K3 will be K2 will be for node 2 and 3, and K3 will be for nodes 3 and 4. So now there are totally a total of 4 nodes. Therefore, the global stiffness matrix GSM, I'll just indicate it as GSM. So that will be K equal to K1 plus K2 plus K3. So K1 plus K2 plus K3, I have to add that. So therefore, there are totally of 4 nodes. So 4 nodes: node number 1, node number 2, node number 3 and node number 4. And node number 1, node number 2, node number 3 and node number 4. So you can just see there are totally 4 nodes. So totally 4 nodes. Okay, so when I try to add this, so to 1 and 1, I'll get here, I have to check this elemental stiffness matrix 1 here. So at 1 and 1, I'm getting it as 7.875. okay, so even this also, how to add, I have explained it in the previous video. You can just check it over that. Next, 2 and 1. At 2 and 1, you don't have any 2 and 1 over here. So 2 and 1 also, I'll get minus 7.875. You can just check that elemental stiffness matrix 1 over here if you're not understanding. 3 and 1, there's nothing but nothing called 3 and 1. 3 and 1 is not connected anywhere, so it will be 0. And 4 and 1 also is not connected anywhere, it will be 0. And 1 and 2 is connected in elemental stiffness matrix 1. So 1 and 2, you will get minus 7.875. So it will be minus 7.875. And similarly 2 and 2 you will get it in here. So 2 and 2 is connected to be 7.875. You can just see in this first thing, 7.875 as well as here 2 and 2 is also connected over here also. 2 and 2 is 4.667 plus this one in elemental stiffness matrix 1, 7.875, 2 and 2. So 7.875 plus 4.667, you can just put it in your calci, you will get 12.542. Next, at 3 and 2, it will be minus 4.667, because 3 and 2 you will get it minus 4.667 directly. Next, 4 and 2 is not connected over anywhere. And next, 1 and 3 is also not connected anywhere. And 2 and 3 is connected here, so it will be minus 4.667. Next, 3 and 3 is connected here as well as here. So 3 and 3, or you get it as 4.667, and 3 and 3 you get it 5.1714. So that if you just add it, you will get 10.381. And 4 and 3, while you are just adding 4 and 3, you will get 5.714. Next, 1 and 4 is not connected anywhere, and 2 and 4 also not connected anywhere. And 3 and 4 you will get it minus 5.714, and 4 and 4 you will get it 5.714. So now we have just got it all. Next is global nodal displacement vector. So global nodal displacement vector, you can write it like this: Q1, Q2, Q3 and Q4, because there are totally 4 nodes. And F is nothing but F1, F2, F3 and F4. F1, F2, F3 and F4. So upon displaying that, you will get, and you can just see in this problem, at node number 1 and node number 4 are totally fixed. Therefore, force at node number 1 and node number 4 will be 0. So forces at node number 1 and node number 4 will be considered as 0. So 0. And what is given to be as force number 2 is nothing but 20 kilonewton. So 20 into 10 to the power of 3, and F3 is 10 to the power of 10 into 10 to the power of 3, because it is given to be 10 kilonewtons. So here it is mentioned in the diagram itself. F2 is 20 kilonewton, 20 into 10 to the power of 3. F3 is 10 into 10 to the power of 3. So upon doing that, you will get it like this. And F4 is also put as 0. So now let's try to substitute everything in step number 4. Step number 4 is nothing but equilibrium condition. Equilibrium condition. So the equilibrium condition formula will be K into Q equal to F. K into Q equal to F. So let me try to write K into Q equal to F, and let's not try to forget this 10 to the power of 5 over here also. So just be very careful, and also this 10 to the power of 5 is common in every elemental stiffness matrices. So let me try to write that. So first K. So K, when I try to write it, I'll get 7.875 minus 7.875 0 and 0 minus 7.875 12.542 minus 4.667 0 and 0 minus 4.667 10.381 minus 5.714 0 0 minus 5.714 and 5.714. So this is something but you have got it for all. And next Q1, Q2, Q3 and Q4. Let me try to mention all those. Q1, Q2, Q3 and Q4. And next F. F at node number 1 will be 0 because it is fixed. F at node number 2 is given 20 kilonewton, and at node number 3 it is 10 kilonewton, and also at node number 4 it is fixed again. So therefore you will get it like this. Now we have to do this apply. The fifth step is applying boundary conditions. So fifth step, applying boundary conditions. So I'll write it BCs. BCs are nothing but boundary conditions. So now, as you know, in this problem it is clearly mentioned in the figure that at node number 1 and node number 3 it's fixed. Therefore node number 1 and node number 4 are fixed. Therefore we have to delete first row and first column and fourth row and fourth column. So the first row, so, and remember to write 10 to the power of 5 over here. So the first column is eliminated because this is the elimination method, and you're going to eliminate first row, and also first column we are going to eliminate, and similarly fourth row we are going to eliminate, and similarly fourth column we are going to eliminate. So, and this is also getting eliminated. Okay, now the remaining elements, or the remaining elements whichever in the matrix, you are going to write it. 12.542 minus 4.667 minus 4.667 and 10.381. So let me try to write this, and Q2 and Q3 also let me write it. So Q2 and Q3, and here let me try to write it 20 into 10 to the power of 3 and 10 into 10 to the power of 3. So let me try to write this as well. So now let me try to apply the matrix multiplication. So it will be this element into this, this into this. Similarly, this element into this, this into this. First row multiplied by first column, second row multiplied by the first column. So you will get 12.542 into Q2. So regarding that order of the matrices, I have told you clearly in the last video, you can just check it out. Minus 4.667 into the Q3, 12.542 into Q2 minus 4.667 into Q3. That is nothing but equal to 20 into 10 raised to 3, and this one multiplied over here, this one here. So minus 4.667 Q2 into Q2 plus 10.381 into Q3. That is nothing but equal to 10 into 10 to the power of 3. So now, as I told in previous problem itself, you have to solve this both problems. So this conditions you will get it in like using the calculator, you will get it. So using the calculator, you can just go to the equation mode form, just put it a number of unknowns as 2, and if you just substitute this as a1, b1, c1, a2, b2, c2, you will get the answers. So I have already solved it. Upon simplification, I'll get the answer as 0.02345 mm. So for that simplification, you can just refer my last video, how to solve this in Calc more equation form. You can just refer to my previous video. In the previous video, I have just clearly solved it. So here I will just solve it in a quicker way. So you can just try to put this in the calculator, you will get the answers. And also don't forget to finally divide your answer with 10 to the power of 5, which you must do it regularly. Okay, so upon solving this, you will get it. So if you wanted to know, you can refer to my video in the previous In the previous video, you can just refer it. So stress in each element. So let's try to find out stress in each element. So there are totally three elements over here: element 1, element 2, and element 3. So element 1 will be E1 divided by L1 minus 1 and 1. So Q1 and Q2. So let me just try to substitute all these values. So element 1 is nothing but 7 into 10 to the power of, so the given, so what is like E1? E1 is nothing but Young's modulus of element 1. Young's modulus of element 1 is 0.7 into 10 to the power of 5. So 0.7 into 10 to the power of 5 divided by L1. L1 is nothing but found to be 80 mm, 80. And so let me just try to put this, and q1 is nothing but 0, because in this problem it is you can just see clearly node 1 and node 4 are fixed, therefore the displacements in the forces acting at node 1 and node 4 will be 0, and also thus the displacement also will be 0, therefore it will be 0 and 0.02345. So upon solving this, so first we have to solve this. So upon first solving this, you will get, so let me just try to put that in calci and just try to tell you. So upon solving that, you can just put that in calci. 0.7 into 10 raised to 5, 0.7 into 10 raised to 5 divided by 80. So so it's divided 0.7 into 10 raised to 5 divided by 80. So I'll get 875. So let me just multiply that 875 inside. I'll get minus 875 and plus 875. And let me just put this 0 and this value as well, 0.2345. So minus 875 into 0 plus 875 into 0.2345. That is what the multiplication of this matrix will be. So I'll just put the arrow marks here. So for multiplication also I have just explained clearly in previous video. So in this video, let me try to write the answer directly. So it will be minus 875 into 0 plus 875 into 0.02345. If you have doubts in multiplication, you can refer to my previous video. So I'll get 875 multiplied by 0.02345. So I'll get 20.51. So stress in element 1 will be 20.51 Newton per mm square, because that is what is given in the question, in Newton per mm square. Now let me try to find out stress in element 2. Stress in element 2 is nothing but given as sigma 2. So sigma 2 is nothing but E2 divided by L2 minus 1 and 1, and here it will be, so for element 2 it will be Q2 and Q3. Q2 and Q3. So E2 is found to be how much it is. E2 is, so let's try to find out. E2 is given as 1.05 and L2 is 90. Okay, E2 is 1.05 into 10 raised to 5, and L2 is 90 minus 1 and 1, and Q2 and Q3. Let's try to find out Q2 and Q3. Q2 is found to be 0.02345, so which we have found out, 0.02345, and Q3 is 0.02017, 0.02017. So let me try to, so upon solving this in calculator, when you put only this number, I'll get 1166.67. So let me just multiply that inside. I'll get 1166.67 and 1166.67 and 0.02345 and 0.02017. So now let me try to multiply this. So I'll get first element multiplied by this element multiplied by this. I'll get 1166.67 multiplied by 0.02345 and plus 1166.67 multiplied by 0.0217. So this, if I just try to multiply, I'll get it like, let me just try to, okay, upon simplification we'll get the answer as minus 3.8266 Newton per mm square. So that is the final answer. So now let me try to do this as sigma 3. Sigma 3 will nothing but stress in element 3. So E3 divided by L3, the formula that minus 1 and 1, Q3 and Q4. Q3 and Q4. So let's try to substitute all those values. So E3 is found to be how much? E3 is 2 into 10 to the power of 5, while L3 is found to be 70. So 2 into 10 to the power of 5. So 2 into 10 to the power of 5 divided by 70 minus 1 and 1, and Q3 and Q4. Q3 is found to be 0.02017 and q4. Q4 is okay, q4, fine, there is nothing but q4. Q4 will nothing but be 0. So because it is, the node is fixed, so as I told you that in the beginning itself, so node is fixed, so as the node will be fixed, so here again we have to solve this, try to put that value over here and try to do the matrix multiplication. So upon solving, we'll get sigma 3 equal to, okay, upon solving, we'll get the answer as sigma 3 equal to minus 57.62 Newton per mm square. It is nothing but the same thing. Just try to do the same common, you have to just put this value. First you have to simplify this value, and then you have to multiply that value inside, and then you have to perform the matrix multiplication. It is nothing but same. Next, let's try to find reaction of the supports. So reaction of the supports, you have like two supports, that is at node 1 and node 4. So we have to find out reaction at node 1 and node 4. So let me try, the formula is nothing but R equal to K into Q minus F. R equal to K into Q minus F. That's what you have to put. Okay, in this we have to find out the reactions at R1 and R4. That is nothing but at node 1 and node 4 we have to find out. So this is nothing but K, global stiffness matrix. This is nothing but Q, and this is nothing but F, KQ minus F. So we have to just multiply this first row with this column and fourth row with this column, because that is only for R1 and R4. So let me just try to do only that one. Therefore 7.875 into 0. So 7.875 into 0. So plus, okay, plus into minus will be minus 7.875 into 0.02345. The first element into multiplied by the first element, second element multiplied by second element. Next, plus 0 multiplied by this. So 0 multiplied by this will be 0 anyways, and again 0 into 0, that will be 0 anyways. So this will, this will just give you that R1 value, and plus that we should also multiply this 10 power 5, and also that we have to subtract with this first element 0. So upon that, so let me try to solve that. So upon solving, so I'll get, this is also found to be 0. So I'll get like 7.875. So minus 7.875 minus 7.875 multiplied by 0.02345. So I'll get so much multiplied by 10 raised to 5. I'll get the first R1 as minus 18,466.875, and the SI unit will be Newton. And similarly, let me try to find out R4. So R4, when I'm trying to do it, it will just be 0 multiplied by this will be 0, and 0 multiplied by this, that is also will be 0. 5 point minus this into this will be minus 5.714, and multiplied by this, because that will be common, 10 to the power of 5 multiplied by 0.02017 minus this one, this third corresponding element. I hope you understood this, because I'm just trying to teach you in as much as quicker as possible here. So minus 5.714 multiplied by 10 raised to 5, and that one let me try to multiply with 0.02017. So, and that answer let me try to multiply with 10 raised to 10 to the power of 3. So the final answer, you will get it R4 as minus 21,525.138 Newton. So thus we have just solved everything in this problem. We have just found out stresses in each element, nodal displacement, and also reaction of the supports. So reaction of the supports are nothing but only at the nodal, only at the nodes 1 and 4. So I hope you understood this problem. See you in some other problem as early as possible. Thank you.